Maximizing the power efficiency of our designs has become critical as more systems get their energy from battery arrays and as we look to high power electronics to supplant traditional combustion based systems. Many of us are looking towards wide bandgap technologies to help us design these systems. But how complex are they to design in, and how do we make cost benefit decisions for those new silicon carbide and gallium nitride based technologies? Technologies like solar inverters, battery charged autonomous vehicles, and electric vehicles have really changed the way that we as electrical engineers have to look at our designs and the efficiency of the power that we use. But even more traditional applications like appliances and even tool recharge circuits, with a lot of regulatory bodies looking at those, have required us to take a look at what happens to the power that comes into our system and maximizing the efficiency of that power to ensure that we can complete the application in the most efficient manner possible. Adding to the complexity of that, also wanting our applications to be able to work on electric grids around the world with different AC voltages coming into them. And you end up with a lot of complexity that we've got to consider in our power architectures and our systems. Now, all these complexities have added and created this new great way of looking at our semiconductors and caused us to look a little bit away from silicon and at new technologies like silicon carbide, like gallium nitride, and what we call wide bandgap technologies for more efficiency and lower impedances in our designs, lower RDS-ons for our MOSFETs, lower voltage drops across our diodes to maximize the capabilities of our systems. But with those new technologies, there are things like a slightly different way of looking at how we do those designs as engineers. And then beyond that, they are more expensive typically than traditional silicon design. So how do we make the decision on when it makes sense to move to a wide bandgap technology for our designs? Today, I have the privilege of speaking with Doug Bailey, who's Vice President of Marketing and Applications at Power Integrations and an expert in this area of technology. Doug, thanks so much for joining us on The Current today. I really appreciate your time.
Well, thank you very much for having me, Todd.
So I think these wide bandgap technologies have been around long enough that we've all started to get fairly familiar with them and some of the basics of them. But what really has led and created the ability for this technology to start thriving and for us to start looking at new ways of using these silicon carbide and gallium nitride technologies?
Yeah, the way I think about silicon carbide and gallium nitride is I think back to my first EE 101 class at university, and the lecturer put up an image of a transistor, and he went through how a transistor works, and the analysis done at that point was all about the ideal transistor. So this transistor had no RDS on, it had no capacitance, it required no gate energy to drive it. It was just basically a switch, and it turns out that, obviously, you learn in the very next class that, there are things like voltage drops and RDS-ons and capacitances, and that you need to take account of those when you design a real circuit. And the way most power supply topologies are designed, they're designed to overcome some kind of imperfect parasitic that is brought on by the relatively poor switches that we were all using, for initially bipolar and most recently silicon MOSFETs.
Right.
The way I think about gallium nitride and silicon carbide is they're both closer to the ideal switch. The capacitance that you have to suffer, the COSS across the source drain, is lower compared to the conductivity. And so you can add a lot more conductivity to your circuit without suffering a penalty from switching losses. And that's the fundamental benefit. It's closer to the ideal switch. And so you can make power supply designs with fewer compromises to efficiency and thermal performance and power delivery.
Yeah, I think that's a great way of looking at it. I mean, really, that's the consideration. It is much more close to that perfect switch that we all start out thinking, oh, this is going to be easy to design in, and then you start realizing there's a lot more complexity involved in that design when you're in the real world and not just looking at a simple schematic design in that electrical engineering 101 class that we all took. So, we kind of that kind of gets into some of the benefits that we've got for silicon carbide and gallium nitride. Of those, technologies, do you think there's a place for both of them out there, or do you think one of them is going to end up winning out over time?
Yeah, that's a very, very interesting question. At the moment, silicon carbide is the volume shipper, and that's because it's been out longer. I think silicon carbide diodes came out maybe 12 years ago or so, and they became very popular very quickly. The low reverse recovery is the main reason that people like the silicon carbide diodes. And then it took a little longer to do MOSFETs, and that's because there's no native oxide. So you have to struggle to build a reliable oxide for a silicon carbide part. If you try and oxidize silicon carbide, you get gas and sand, which is not helpful. So you have to build an oxide for the gate. Anyway, that problem seems to have been solved. People have become very comfortable using silicon carbide. In fact, major automobile companies are now using silicon carbide in their EV inverters. And the world has moved to a point where silicon carbide's fine. Gallium nitride is relatively new. We launched our first product in 2018. And there were a couple of guys at lower voltages who launched even before that. So it's still a relatively new technology. But in my view, it's better. It's a better technology than silicon carbide, particularly at low voltages. And by low voltages, I mean mains connected kinds of voltages. So what I anticipate is that gallium nitride will supplant silicon carbide in lower voltage applications like your mains connected devices. The manufacturing technology of GaN is cheaper than silicon carbide. And the way to think about that is energy budget. It turns out, silicon, carbon, even gallium's not a rare earth element. Nitrogen's obviously around. So none of the chemicals are in short supply worldwide. So that's not where the cost is. The cost is in the energy budget required to process the materials, to create the wafers, to do the epi, and so on.
Right.
And silicon carbide loses on that score. It's a material that requires an awful lot of energy to process. And so in my view, silicon carbide will always be a more expensive technology than gallium nitride because of the energy budget requirement. So then it boils down to, well, I guess, if GaN can do it, it should do it because it's cheaper. And the way that's working is GaN is starting at the lower voltages, and I think it's going to sweep up into higher voltages as time passes, likely supplanting silicon carbide from the lower voltage end up and up, and there'll be some kind of a truce formed at some point. Don't know what voltage that level is going to be at, but it'll be silicon carbide above a certain voltage and gallium nitride below, in my opinion.
Right. That makes sense. Now, are switching speeds going to play into that at all from that standpoint?
I don't think so. Both silicon carbide and gallium nitride offer higher switching speeds than silicon alone. And I think that both of them surpass the capability of the magnetics components by quite a large margin. And so you really don't worry too much about switching for either of the new technologies. It's the magnetics that hold us back. And I think that we're bumping against some fundamental laws of the universe there that are going to be really hard to solve. So, most of the time we worry about slowing down the GaN and silicon carbide switches that we use rather than attempting to leverage their high speed.
Right. Makes sense. And then as far as applications, we kind of talk about, we're kind of talking about the future and where things are going. And it sounds like definitely GaN seems to have a leg up as time goes by on being maybe the technology that wins a wider swath of the market. But if a customer was looking at applications today, what kind of applications would you steer them towards? Maybe you should go with silicon carbide for these kinds of applications today. And maybe in these kinds of applications, you should be looking more at GaN.
Yeah, we're in I think, a unique position. We have a product line called the InnoSwitch 3, and that leverages silicon, gallium nitride, and silicon carbide all in the same product family. So it's the same controller. It's maybe I should start at the beginning. It's a flyback power supply chip, and it's got a controller on the primary switch, the secondary controller, and then a built-in magnetoelectric couple that we call flux link that communicates from the secondary to the primary and allows for the synchronization of the synchronous rectifier and the main and the primary switch. So that product line for 30 watts and below, approximately 30 watts and below, we recommend a silicon switch. And the main reason for that is that the gallium nitride switch is so small that it's hard to pick up, and the periphery of the transistor takes up such a high proportion of the area that it really doesn't help very much. Also, the package we use is thermally very efficient anyway, and so a 92, 93% efficient switcher in the package we're using at 30 watts doesn't dissipate a lot of energy anyway, and so silicon's the right choice. But if you go over 30 watts, at mains kind of power voltage levels, something in the 300 to 400 volt main bus level, we recommend gallium nitride. The gallium nitride can go up to 200 watts quite comfortably in a tiny surface mount package. Does a great job, and that's what we see as the future for the higher power levels for flybacks. And then we have a silicon carbide in exactly the same package with exactly the same controllers. And the silicon carbide is used for high voltage applications. It's a 1700 volt silicon carbide device. Right. And we would use that in applications like 800 volt bus automotive. So it's inside an automotive inverter. It needs to be an emergency power supply. And the reason for an emergency power supply is if the 12 volt battery connection falls off the inverter needs to be able to generate power for the controller so you don't end up with an undefined situation for the IGBTs or SiC MOSFETs inside the inverter. So that needs to be a very reliable, very robust, high voltage power supply, and that's what we use this InnoSwitch 3 with a silicon carbide device for, and that's become quite popular. And then in any other 800 volt application, the 1700 volt switch is really does a fabulous job. So in an EV, you may see it in the air conditioning systems, for example. That's a high voltage system. So anywhere where you need to convert the high voltage bus down to something suitable for the electronics, for the CAN bus or the controllers, that's a PI specialty is sipping from a fire hose, right? That's what we help engineers to do.
Right. Makes sense. So with all of that, and when you're looking at those types of circuits, whether it's an HVAC or some of the motor drive, a solar inverter, things along those lines, that we maybe are as electrical engineers, maybe we're familiar with doing that in a high-powered silicon MOSFET design. Is it more complex to do a design with silicon carbide or GaN? Or are there other considerations that the engineer needs to be taking into account? Or is it pretty much the same with just those lower RDS-ons that we've talked about?
Yeah, that's an interesting question. The answer is yes and no. Yes, it is more complex to use gallium nitride or silicon carbide, and that's because the devices switch faster and they need a little bit more babying and management to work at all, and a lot more to get the best out of them. What we've done with our product, I mentioned this product before, that's the device that can have either silicon, gallium nitride, or silicon carbide in it as the main switch. is we've done the hard work. So we're controlling these devices very carefully. We're managing them well, and so from the external point of view, a developer wouldn't see any difference. In fact, it's quite funny. You put the drain waveforms on a scope for the product, and you can't tell from a scope image whether it's silicon or gallium nitride or silicon carbide. You just can't tell. The
Right.
only the giveaway for GaN is that it jumps up 1.5% in efficiency from
Right.
92 to around 93.5. And for silicon carbide, your drain waveform is going to be at over 1,000 volts. So those are the giveaways. But from the wave shape point of view, you can't tell. So we've taken the difficulty out of it for the engineers, and we're serving up a product that can get them into gallium nitride or silicon carbide without a lengthy development process. It's completely painless to use one of these advanced technologies rather than the worry. So that's my advice is to choose when you want to use one of these kinds of technologies is to choose a highly integrated solution where somebody else, like Power Integrations, has done the work for you to deal with the switching speeds and the other more challenging aspects of using the new technology.
Right, right. And so, along those lines, what are some of the things that Power Integrations has done to make working with these systems easier for design engineers?
Um, Probably the most obvious thing is the integration. By putting it in the same package with the controller, we've taken away a lot of the parasitic loops. You get in a power supply. One of the tricks is to make sure that these switching loops are very short, so you don't excite parasitic inductances and capacitances, and or generate a lot of EMI. You can think of the wires on the PCB as an antenna to a large extent, and so you're switching high voltages and high currents through these little antennae, and and that radiates. And there are regulations as well as good sense that says you really shouldn't be radiating a lot of energy from a power supply. So integration is what matters and is the biggest benefit. I think other people are learning that who have discrete devices, but we've always been an integrated device company, and so even our silicon devices have small loops. So it wasn't as big a leap for us as perhaps it was for folks who were coming at this fresh from a discrete transistor point of view.
Right, right. What do you see as kind of the inflection point? I mean, because obviously, if you're doing something with a wide band gap, it is going to be a little bit more expensive. And then we've talked about a little bit more complexity involved in designing the circuit. Do you see an inflection point for an engineer on when they should be looking at wide band gap technology versus silicon? Maybe as far as the efficiency required in the system or the costs that their market will bear?
Okay, so I think I'm going to challenge you on the more expensive part.
Okay.
The initially when a new technology has been launched, it tends to be a little bit more expensive until the volumes start coming up. I mean, the semiconductor industry is a spectacular industry from the point of view of cost reduction and scaling and size, bringing costs down. And it turns out that gallium nitride has already crossed that boundary. So from a PI point of view, from PI products point of view, we're already lower cost with gallium nitride than we are with silicon
Right.
for the power levels where gallium nitride plays a role. So that's in the mid power, the 50, 60 watt up to 200 watt adapters. You're really better off using a gallium nitride solution because it saves so much trouble. You can go with a 2-layer PCB instead of maybe a 4 or 6-layer PCB. You can
Right.
go with smaller transformers. You can go with, you can maybe save a little bit on your capacitors. You certainly don't need heat sinks right? And so all of that system level cost adds up. And so if you do the math, gallium nitride is the way to go for these medium power mains voltage level power supplies up to certainly 200 watts.
Yeah, I love getting a chance to change the perception out there, because I think that is the perception, is that, oh, if I go with these new technologies, it's going to be more expensive to my system. So to hear that, and to hear that that's already starting to change, is really, really exciting. And I think something that we as engineers have to, really accelerate our embrace of these different technologies, and look at them in designs that we may think that, oh, I don't need wide bandgap there. Well, it may make a lot of sense to go ahead and make that change. So that's incredibly exciting to hear. Thank you very much for
Yeah.
that. So,
Well,
Doug,
I,
thanks so
I
much for sharing your expertise today. Really appreciate you being here on the current. And this was incredibly informative for me, as we continue to look at these wide bandgap technologies and where it's going to be an impactful technology across all of our embedded designs. I think that's definitely expanding, as you've just shown there. Thanks also to our audience for joining us today on this episode of The Current. Really appreciate you being here and being part of what we're trying to do here at Future Electronics. If you have designs that you're looking at using wide bandgap in your designs, we've got teams of engineers, our analog and power specialist engineers, our generalist engineers as well, who are really getting an expertise in this. We would love to work alongside your engineers, introduce you to experts like Doug from PI and others, to help you be successful in those designs. Please reach out to us at shapingthefuture@futureelectronics.com. Again, that's one word, shapingthefuture@futureelectronics.com. We would absolutely love to support you in your designs. Doug, thanks again so much for being here with me today. Really appreciate your time, and we'll look forward to seeing all of you next time on The Current.
Thank you very much, Todd. It's been a pleasure.